Somit, can I start or shall we wait for some more time?
I think you can give a minute and a half, and then you can start.
Okay.
Okay. I think we can start now.
You can start. Yes. Hello everyone. Welcome to the Department of Chemistry, IIT Delhi. Thank you very much for joining this webinar today. My name is Janikiram Vaitla, Assistant Professor at the Department of Chemistry, IIT Delhi. And we are very pleased to bring you this content today, which is a part of the online Pratidhwani series that the department is organizing. Under Pratidhwani, we invite eminent scientists from the different areas of chemistry from all around the world. These 30-minute talks are held every Thursday afternoon. Please do check out our webinar website. You can also find the link in our flyer emails and also on our department website. The webinar series is sponsored by OtherCafe. OtherCafe is an online platform that aids with the writing, collecting, organizing, collaborating, and publishing your research content through features and integrations with the products like Mendeley, Jotero, Orchid, Crossref, and so on. Think of it like Google Docs, special designed and developed for the academic community, and much more. Before we start this webinar, a couple of technical details. Please do unmute yourself during the talk. If you have any questions, please type them in the chat box and we will try to get at least some of them to the speaker after finishing his talk. Before start the webinar, I would like to give you a brief introduction about Professor Davies. Professor Davies did his PhD from University of East Anglia and a postdoc from Princeton University, USA. He began his independent academic career at Wake Forest University. In 1995, he moved to the University of Buffalo, where he held the positions of UB Distinguished Professor and Larkin Professor of Organic Chemistry. In 2008, he joined the faculty at Emory University as the Arthur Griggs Candler Professor of Chemistry. He is currently the director of the NSF Center for Selective Stage Functionalization, which brings together 23 faculty members from 15 topmost universities in USA. This program covers the design of chiral catalysts, the development of a new synthetic methodology, total synthesis of biologically active natural products, and development of chiral therapeutic agents. A major current theme in his group is catalytic asymmetric stage functionalization by means of rhodium carbonate-induced stage insertion. The impact of his carbonate chemistry was recognized as he was chosen to be the recipient of the 2013 Heroes Reagent of the Year Award. Other awards include American Chemical Society Hope Scholar Award, Fellow of the Royal Society of Chemistry, Fellow of the American Chemical Society, Fellow of the American Association for the Advancement of Science, and Fellow of the National Academy of Inventors, and so on. The list is so big. Today, he is going to give a talk on catalyst controlled site selective and enantiomer selective stage functionalization. A very warm welcome, and over to you, Professor Davies.
Thank you very much, Janakiram. It's great to be here. It's great to see you. You were one of the brilliant postdocs we had in the group, and you had a huge impact on our group. And I'm really pleased to see you starting your independent career at this stage. Thank you all for coming to join this talk. The way of doing these virtual meetings really allows international connections to be built and to get a good sharing of science between different countries, even though it's hard to travel these days. So what I want to talk to you is our approach to do CH functionalization. And I'm very fortunate to be actually the leader of this NSF Center for Selective CH Functionalization. So I'm a synthetic organic chemist, but I'm able to collaborate with many different types of scientists to really try to push the field of CH functionalization. And today's story is going to focus a lot on the catalysts that we've developed. And even though at this stage we've collaborated with virtually everyone in the center, there's 22 professors from 15 universities. What I'm going to concentrate on is our collaborations with my colleague Jamal Musayev at Emory and Ken Hauk in terms of the computational understanding of these catalysts. Some collaborations with Jin Kuan Yu from Scripps, Brian Stoltz from Caltech, and my colleague Simon Blakey, using the new methodology towards total synthesis and building chiral fragments. And then we also collaborate with industry too. So I'll show you some industrial applications involving collaboration with AbbVie and Novartis. Okay, so what's so hard about CH functionalization? Why is everyone interested in CH functionalization? Well, of course, the thing about CH functionalization, it's tough because you've got to have a reagent that's reactive enough that can react with a CH bond. Yet most molecules, organic molecules, have multiple CH bonds. So how are you going to get site selectivity in the chemistry? We know there's free radical chemistry that's around. There's some industrial processes, of course, that involve converting alkanes into larger alkanes for petroleum, for example. But still, getting the site selectivity is a major challenge. And so one of the approaches, of course, is to rely on the substrate control. That's how you do radical functionalization of alkanes, for example. And there's lots of really modern radical processes available these days, a lot of photoredox chemistry, for example. But that still requires a substrate to be the controlling element. An area that's become very popular is to use a directing group. So there you have some feature in the molecule that will actually coordinate to a metal catalyst. And when that coordination happens, it places the metal close to one specific CH bond so that you can get selective reactions. And this has developed now into a really powerful way. But in terms of full control, obviously relying a lot on the substrates, sort of unusual functional groups, if you like, that allows the chemistry to go. So what the center wants to do is go to the next area. And what we think is really important is to have catalyst control. So, for example, Jin Kuan Yu is in our center. And the way that he approaches this is he has a weak directing group now. And so allows the metal with its ligands to do the control of which CH bond is functionalized, rather than it being dominated by the directing group itself. And then our approach is to have no directing groups at all, relying purely on the catalyst and its shape to control the site selectivity. So I thought I'd try to show you in this visual what I'm trying to talk about. So if you have an alkane like this, obviously thinking about getting controlled chemistry on this might be thought about being quite challenging. And so what we need to have is a suitable reagent that will allow a functionalization of a CH bond in that system. And then we could design particular catalysts to select which CH bond. So these catalysts will have defined shape. It could go for this methylene site that I've shown you in blue. You could get a less bulky catalyst that will go for the tertiary site, as I've shown you in green. Or you could get an incredibly bulky catalyst that will go for the primary CH bond, as I've shown you in pink. Or you could be even more selective, so you can distinguish between, say, different types of methylene groups by using the right shape of catalyst. And so even though this looks a little bit like science fiction, these are actually diagrams of pictures of actual catalysts that we've developed that can actually achieve this type of site selectivity. Okay, so the way we do our chemistry involves transient metal carbines. It's different from the conventional way of doing CH functionalization or CH activation, where in traditional CH activation, the metal inserts into the CH bond. And then you've got this organometallic species that now needs to undergo a catalytic cycle to complete the reaction. Our approach is different. So we use diazo compounds, and in the presence of our catalyst, we will lose nitrogen and generate a very reactive metal carbene intermediate. that is quite capable of doing a CH functionalization, even of unactivated CH bonds, but it inserts the metal into the CH bond. Sorry, it inserts the carbene into the CH bond rather than the metal. The challenge, of course, is to do this selectively, okay? And in the past, the way this was done was to do the chemistry intramolecularly. That's the way you tackle things where it's difficult to get selectivity. But we wanted to do intermolecular chemistry. And the way we've done that is by two control elements. One is to modify the typical metal carbenes that people use so that they can still do CH functionalization, but they're not so outrageously reactive now, so that then you can use the metal and the complex that you have to do the controlling of the chemistry. So it turned out the development of this new class of carbenes to do this chemistry was actually something I did very early in my career. So when I started in the mid-1980s, the traditional transient metal carbenes came from compounds that had one or two electron withdrawing groups, like diazoacetate, for example, or diazomalonate. And this class of carbene has very little back bonding, so it's already very electrophilic, and with additional electron withdrawing groups makes it incredibly reactive. So I won't go into the detail, but early in my career, we started working with vinyl carbenes, and we realized the vinyl group as a less electron withdrawing group, a donor group, actually has very different types of chemistry. What we found is, for example, in this cyclopropanation, unless the normal carbene that gives very poor diastereoselectivity, when you add a donor group, it's incredibly diastereoselective. So we saw a lot of unusual selectivity with this class of carbenes. And so we coined this concept, this donor acceptor carbene, as a new class. And what we found is that it is much more selective than the conventional carbenes. So the other component, of course, is the catalyst. And so, and we've been very interested in chiral catalysts for a long time. So our first generation catalyst was developed in the mid-1990s. This is rhodium DOS, which is a prolinate-based catalyst. And it is a very versatile catalyst. Pretty soon thereafter, we discovered the donor acceptor carbenes with this DOS catalyst give you very high and anti-selective CH functionalization of activated CH bonds, so benzylic or allylic or alpha-2 oxygen, for example. And indeed, we have about 46 papers just on rhodium DOS as the catalyst. So we were a one catalyst group for a very long time. But more recently, we've developed two other generations of catalysts. One, we're often inspired by what our chemistry allows us to do to make new ligands. So we were able to do CH functionalization of adamantane that led to this second generation catalyst. And then our third generation catalyst comes from our ability to do asymmetric cyclopropanation really nicely of this 1,1-diaryl ethylene. So we generated these triaryl cyclopropane carboxylates as catalysts as well. And in recent years, and I'm showing this in red boxes, we've redesigned these even further so that they are now very effective catalysts for site-selective CH functionalization. Now, one of the interesting aspects of these catalysts is that when we developed rhodium DOS, it was difficult to explain why it was such an exceptional catalyst with the donor acceptor carbenes. So back in 1996, we made this rather bold assumption that if you have a big group here around these dirhodium tetracarboxylate systems, then this group will have a preference of either being on the top side of the molecule or the other. And as a consequence, they could self-assembly to generate catalysts that are higher symmetry than the ligands themselves. So if that group was on the top side all the way around, it'd be C4 symmetric. If it was up, down, it'd be D2 symmetric. If it was 2 down, 2 up, it'd be C2 symmetric. And later on, it was realized that you could have the groups all 4 up, but if they interacted with each other, you could break the symmetry and do C2 symmetric. So back at that time, we made the proposal that DOS behaves as D2 symmetric, which was why it was such a good catalyst. It's still a question whether DOSP is flexible enough to take up this D2 symmetric structure, but it turns out our new catalysts really follow this sort of design element for high symmetry catalysts. So, for example, our second generation catalysts, and the first one we developed was this, what we call tetrachloropetide. They all adopt a C4 symmetric structure. So you can see that tetrachlorophenyl ring is on the same side all the way around. We've actually developed further generations of these, so they basically adopt a bowl. And here's a second generation, a deeper bowl. So what's going to happen here is the carbene will bind to the rhodium, and then you've got all of this scaffold around that's going to control the selectivity. And recently, we've gone a little crazy. So let me just show you what we've done. These are some examples of some of the newer bowls we've developed. So always with this type of system, these are all X-ray structures. It adopts this C4 symmetric structure. Our third generation catalyst is a little bit more flexible in what they can do. So, for example, if you have a triaryl cyclopropane unsubstituted or with a para-substituent, what you observe is that that group, and here they are, the four groups are on the same side, but you can see there's pi stacking between them. That breaks the symmetry. So that's, instead of C4, these are C2 symmetric. If you sort of add more sterics to this, you can block this possibility of pi stacking. So, for example, if you go to 3,5 disubstitute, this is so big that if you have one group on one side, the next one to it has to be on the opposite side. So this goes in the up-down arrangement, and that generates a D2 symmetric shape. And then we also found, this was rather surprising, if you had an orthochloro substituent in the system, then that catalyst always adopts a C4 symmetric structure. So there's no pi stacking in this, so that's a regular C4 symmetric. Okay, so with these catalysts, what we've been able to do is break the problem of actually distinguishing between different CH bonds in alkanes, for example. So what we can do is we can do this particular catalyst will do an asymmetric CH functionalization at the most accessible methylene site. This next catalyst will do selective CH. This is a less crowded catalyst. We'll do selective CH functionalization at the less crowded tertiary CH bond. And then we've developed a very bulky catalyst that overwhelms the normal preference for tertiary or secondary. So this catalyst will do selective reactions at a primary CH bond. So what that means then, the size of the catalyst gives you this type of distinction. And we've even been able to take it further to actually distinguish between different types of secondary CH bonds. So I'm going to show you a little bit more detail of that. So we obviously, if you had a substrate like this, you would think that the benzylic should be preferred, electronically really preferred. But we can get a catalyst that will go for the most accessible, unactivated methylene site, overwhelming the steric preference. And that's the catalyst is one of these C4 symmetric orthochlorocatalysts. And then we've also been able to desymmetrize cyclohexanes. Normally, this would be considered a very challenging problem for CH functionalization, particularly if there's no electronic bias to the R group. But we can get a chemistry that will desymmetrize them at this position. And this is another of the second generation really bulky C4 symmetric catalysts. Okay, so let me just show you a little bit more detail about how the chemistry works in this case. So as I said, the orthochloro has been a very special feature for us because what we find when you have an orthochloro is you always get the C4 symmetric structure. And also there is an induced chiral center generated in this system because there's basically a hindered rotation around this bond in the catalyst. And so if you look at each ligand, the chlorine is always on the left, on the right-hand side of the structure as you go around. And what that means is that it has an induced chirality here, which helps with the asymmetric induction. And indeed, in terms of breaking the sort of pattern, the 5-bromo derivative is the best one for site selectivity, for enantiomer selectivity. All of these catalysts operate in the same way. Okay, so just to illustrate that concept to you, So a regular catalyst for us would be this tetrachloropetad. This is not a very sterically crowded catalyst. So as you'd expect, the chemistry will occur at the benzylic position. That's what all this brown material is. And the reaction is not just site selective, it's diastereoselective and enantioselective as well. In contrast, if you do the reactions with the triaryl cyclopropane carboxylates, this orthochloro system, then the chemistry totally changes. It goes for this unactivated but sterically more accessible bond. And you can see it also is highly diastereoselective and enantioselective as well. And so this basic reaction works with a variety of substrates. This just illustrates some of the substrates that shows it always going for the most unactivated bond types of functionality that's present. And what's really neat in our center is we meet every day. We'll be having a meeting later on today where all the people from the center come together, and everyone is throwing ideas on how to, enhance the chemistry. So Brian Stoltz was in the audience when we showed this result, and he suggested, well, there's a really good natural product you could think about going for with this type of unusual chemistry. And so these are the cylindrocyclophanes. And so what we did collaboratively is do some model studies to see whether we could get into this framework. So we start off with one of our CH functionalization reactions. We use that to make the diazo, where we do this palladium catalyzed reaction. But the big reaction we had to do is the following. We needed this carbene to react with this CH bond. And it turns out it works very well. You need a slight excess of this material, but you can see you get good yield, good site selectivity, good diastereoselectivity, and good enantioselectivity. Then the next step is another one of our palladium catalyzed CH functionalization to generate the other diazo. And now we need this carbene to find this CH bond. And this also works really well. And the thing that's interesting about this reaction is that the site selectivity is great. The enantioselectivity is much better because you're doing the second CH asymmetric reaction that enriches the system. But that is at the cost of diastereoselectivity. And so having established that, we're actually at this stage very close to completing the total synthesis. Now, of course, this slide looks really overwhelming. So I just want to focus on the squares because what we're trying to do here is show how you can do sequential CH functionalization to make complex molecules. So this is a primary CH functionalization. So that's using one of our really bulky catalysts. That goes with very high enantioselectivity. Then we use our palladium catalyzed reaction to make the diazo. This is now the big reaction with this carbene has to find this CH bond. That works just fine. And then we make the second diazo. Now this is the next big reaction where this carbene needs to find this CH bond. And that also works very well. This material now is in antimeric pure due to the second reaction that's done, CH functionalization that's done. And then later on, we need to do a fourfold CH acetoxylation. So Jin Kuan Yu joined the collaboration because this was a challenging reaction. And this was a new ligand that he developed for his chemistry that allowed this to proceed very smoothly. So I'm just focusing on the CH functionalization steps to show you how now modern CH functionalization can really impact how you can think about synthetic strategy. So the other challenge for us is we've looked at this cyclohexane. This is a well-known problem, okay, for unactivated alkyl substituted cyclohexanes. So these are some of the best reactions out there, and you can see they're giving mixtures of products. Don't really have time to analyze those in detail. In contrast, when we used our chemistry, it was pretty amazing because what we found is that the chemistry went really cleanly for C3 versus C4, even though sterically there's not much difference between those two. And also the reaction was very diastereoselective because it didn't react with C5. In other words, it didn't react much with C5. In other words, you got a desymmetrization of this tertiary butyl cyclohexane. And once again, these catalysts, we tend to forget about this, are really effective chiral catalysts as well. So this goes with very high enantioselectivity. And again, we've done many examples of this. I just don't want to dwell too much on it. So we're focusing on the diastereoselectivity because that's the key desymmetrization. So you can see it's working pretty well across the board. Obviously, the smaller group, the less desymmetrization you get. But as you get to bigger groups, it works really well. We've also worked with a range of aldehyde-acetates. We've expanded it more recently to other classes of carbene systems. It works really well. And you can also bring a variety of heterocycles as compatible with this chemistry as well, adding an extra interesting element to the chemistry. So basically what we've been doing over the last few years is actually developing the toolbox of catalysts, okay? So that we can take us with the idea that you take a substrate and then be able to decide, oh, this is going to be the best catalyst for the CH functionalization at a particular site. So this illustrates just some of our catalysts, and these are some of our seminal papers that develop the key understanding of what is the site selectivity we can achieve. So having achieved that, now we need to, what we're doing now is thinking about, well, how can we use this now, having understood how these catalysts work, to generate useful products? So my collaborator, Simon Blakey, is interested in metal catalyzed reactions that use chiral dienes as ligands. But many of you would know that those ligands, chiral dienes, are often quite problematic to synthesize. So we became interested with the idea, could we take cyclooctadiene and do a double CH functionalization to generate C2 symmetric ligands that might be of interest in asymmetric catalysis? And so, that looks a pretty simple type of idea. You just got to do, allylic is very active, so 2 reactions, you'd get the product. But if you think about it, it's pretty tricky because the first CH functionalization needs to avoid doing cyclopropanation. That's definitely a potential side reaction. And then once you've done the first reaction, then you've got to be able to distinguish between the 3 allylic sites that are available to do the second CH functionalization. And if these are going to be useful chiral ligands, you need to control the stereochemistry at 4 stereocenters during this whole process. So, of course, at the moment now we've got a toolbox of catalysts. So we could test cyclooctadiene with those catalysts, and it turns out that some of them didn't perform very well, but we did find that the orthochloro catalysts were really good at this reaction. And just to illustrate what we can do, so we've generated a variety of systems where you can get very high in anti-selectivity, the desired site selectivity. The diastereoselectivity is lower because, again, you've got Horo's principle here. So the first CH functionalization goes in 90% EE. When you do the second one, the product now is greater than 99% EE because the other enantiomer from the first generates predominantly a diastereomer in the second reaction. And so these ligands, they're obviously with an ester group, you can diversify them quite a bit further. And in collaboration with the Blakey group, they performed quite nicely as chiral ligands, giving about 70% EE in the subsequent reaction. The other thing that we've done is think about these as strategically change the site selectivity and also develop products that could be thought of as strategically equivalent from more of the classic approaches to put molecules together. And this was where Dr. Janakiran Vaitla really sort of highlighted some aspects of this in the group. So an interesting reaction is a substrate like this, where there's 2 allylic sites, alpha to oxygen, and this one less electronically activated. So normally you'd expect the carbene chemistry to go here, but again, you've got this steric control coming in. And so what was found is that the chemistry prefers to occur at the distal position. And this would be an equivalent reaction to an asymmetric vanillus Michael addition followed by a reduction. And this one reaction was very much under catalyst control. And it turned out there was 2 approaches taken with this. So one is to use the diazo as a carbene precursor, and one of the bowl-shaped catalysts was the best catalyst for the reaction when this was a trans double bond. And then our other approach to make carbenes is to start with triazoles. And it turned out when the double bond was cis, then this particular catalyst here, the catalyst we call NTTL, was the best one, giving you really highly enantioselective, site-selective, and diastereoselective selective reactions. I also mentioned that we think that CH functionalization has got a great potential for developing chiral scaffolds to pharmaceutically interesting targets. And so we worked in collaboration with several academic groups as well as pharmaceutical companies to illustrate this concept. And we're particularly interested in substrates where there are multiple CH bonds, but hopefully our catalyst will control it. So let me just very briefly illustrate this. This is a collaboration with AbbVie. So these are reactions on cycloalkanes, okay? And the catalyst that works really well here is this tetraphenyl thalidomide catalyst. This adopts the C4 symmetric bowl shape. And what that catalyst does, as you can see, with these silocyclobutanes, is give you really high enantioselectivity, going for this position. And then you can even do desymmetrization when you're doing the reaction in a silocyclopentane derivative. Again, you see you're getting high diastereoselective selectivity because it's choosing this position over the other, as well as high enantioselectivity. And you can even get good diastereoselective selectivity if you've got two different groups on the silocyclobutane. Again, you get excellent control in that case. Another structure that's of great pharmaceutical interest these days is these bicyclopentanes. They're considered as a pharmacophore for an equivalent to a benzene ring. And so there's a bioisosteer that's commonly used, but they're quite difficult to make chiral derivatives. Again, we can do very nice, using one of our less crowded catalysts, we can get reactions at the tertiary site in the presence of a variety of different functionalities, showing the types of selectivity that's possible. Of course, on occasion, we can have a problem. So let me illustrate the problem. So if you do a reaction on this compound that's got a benzylic methyl and the tertiary site, what we find when we do the reaction with the regular catalyst is we get a mess. We basically get reaction at the tertiary site, reaction at the primary benzylic, and we also get double addition. So not a very attractive reaction. However, we can control that because if we do the chemistry with one of our more bulky catalysts, then the chemistry stops at the tertiary site. So now it becomes just a benzylic CH functionalization and goes with very high enantioselectivity. So what that means is that if you want to, you can start with this substrate, you can do a reaction with a bulky catalyst that will go for the benzylic, and you can follow up with a reaction with a less bulky catalyst that will go at the tertiary site. So you can introduce two functionalities here. And of course, if you change the order, then you can change the position of the bromo and the trifluoromethyl in this case. Now, I'm not saying that these are drug candidates, but if for some reason a company was building around this type of structure, then trying to make them any other way other than this way would be very difficult indeed. Okay, so for us, this type of system is more interesting because now we've got to choose between two potentially reactive positions, this tertiary site and then the most accessible secondary site. So not surprisingly, if we use one of our less bulky catalysts, it's going to go for the tertiary site. And here are a few examples of this, very highly enantioselective. In contrast, if you use one of our bulkier catalysts, and we really do like this orthochlorocatalyst these days, then the chemistry is going to occur at the less crowded site. And you can see now we get these three substituted products rather than the one substituted product. And then one final example is this piperidine system. So this has three distinct CH bonds. Now, in our original development with DOSP, then this would be a reasonable site of attack because it's activated next to the nitrogen. What we're interested in is whether we can use our sterics to get into the other, our more sterically crowded catalyst to get into the other positions for functionalization. So not surprising then, if you use one of our less bulky catalysts, so we consider the tetrachloropetad as one of our less bulky catalysts, then the chemistry goes pretty nicely at C2. That's pretty standard for us. Now the challenge is, can we change the chemistry around? And so what we found, again, we like that orthochlorocatalyst once again, then that drives the chemistry towards C4. We found it was even better if you made this somewhat more electron withdrawing, so using this as a protecting group on nitrogen. and then we could get very nice C4 functionalization. Now, the real home run for this chemistry would be if you could do it at C3, because that is not electronically preferred, and there's no steric bias that would drive this. We still haven't got a catalyst that will cleanly do this, so we have to do this indirectly. And the way we do that actually is back to the first generation catalyst, but the way we do it is that we actually start off with a double bond in this case. In other words, we make the cyclopropane, and then we do a reductive ring opening of the cyclopropane to get the 3 substituted product. Now, I should mention that 2 substitute products of this general type, an example of that type of compound is actually a pharmaceutical drug called Ritalin. And so these are all Ritalin type analogs, so pretty interesting in what their biological activity might be. Okay, so what I've tried to show you today then is that we've developed these toolbox of catalysts, and we've done a lot of mechanistic work across the center to really understand how these catalysts work, which is beyond today's topic. But with this family of catalysts, we began doing fundamental studies to understand the selectivity profile that is possible. And so now we've transitioned into really thinking about how to use these catalysts. We're still designing new ones, but trying to use these catalysts to show how they can really impact very quickly synthesis of novel scaffolds, either in a total synthesis strategy or as pharmaceutical building blocks, or in terms of making new generation chiral ligands. Okay, so let me finish off by acknowledging the wonderful group of students that I've had in my group. They've been brilliant, actually, because not only are they responsible for their own research projects in the group, they often lead the collaborations we have with many, many different academic groups within the center and beyond the center, some international groups as well as our industrial collaborations. And I also want to acknowledge the wonderful work that the center has done with this sort of strange looking graph that I have here. What this is showing is actually the number of collaborative papers where there's at least 2 senior investigators that have been published by the center. So the ones here are the collaborations between center members. These are collaborations with other domestic scientists, many others, a lot of international collaborations, as well as some industrial collaborations as well. And so it's been really exciting where you, instead of taking the attitude, I own my chemistry, I don't share it with anyone, people are really looking to really expand the power of the science they're doing through this broad scale collaboration. And frankly, it makes it a much more interesting environment to do science rather than be isolated in your own research group. Finally, I'd like to thank you for your attention, and if people have any questions, I'll be happy to answer them.
Thank you, Professor Davies, for the insightful and stimulating talk. I hope many students and faculty enjoyed your talk. It is interesting to see that the toolbox of rhodium catalyst with the donor acceptor carbines show that it is indeed possible to achieve site-selective CH functionation at unactivated CH bonds without restoring to the use of directing groups on the substrates. It's really interesting. There are some questions from the students in the chat box. Can I ask that one?
Oh, yes, go ahead. Sure.
Yeah. The first question is from Premanand Ghosh. In case of dissymmetrization of cyclohexane, how much it is useful to dissymmetrize any other position? Any particular reason to choose that particular position in cyclohexane?
Yeah, so when we were doing the reaction on cyclohexane, that was set up as sort of a fundamental challenge. You know, if you look in the literature, this would have been thought to be impossible to achieve. And so basically, we challenged whether this could be done. And of course, we've discovered that. And we're also re-exploring whether now we can, in terms of catalyst control, can we indeed get C4 functionalization? Can we modify it in an appropriate way? But that was really, you know, not seen initially as a synthetically useful product, but as a very important challenge of the chemistry. Once we have learned that, now we are thinking about what other types of molecules could we desymmetrize that would be much more synthetically useful, if you like, having learned the lesson from cyclohexane.
Another question from Subrata. How important is the rhodium-rhodium bond? Does this metal bond has any involvement in the reaction mechanism?
Yeah, so the rhodium bond. So obviously, rhodium's expensive, and you're using two rhodiums, so it's even worse. So we've looked at many other lantern type structures. We have an inorganic chemist named John Berry, who's one of the world experts in the inorganic aspects of these lantern compounds, and we find that the dirhodium catalyst is quite phenomenal for this chemistry. So the other rhodium has an important role to play. It helps in driving off the nitrogen to make the carbene. So the activation energy for that reaction is very low. But then it has this role with very limited back bonding, so it makes the carbene very reactive. So particularly in cyclopropanation chemistry, this catalyst will, in 2 seconds, do 1,000 turnovers at room temperature. And we have taken this catalyst down to loading as low as 0.00005 mole percent and still get an effective reaction. So, and no other metal catalyst will perform anywhere near this. There are a lot of metal catalysts for decomposing diazo compounds, but there are very few of them that do anything with CH functionalization, particularly intermolecular CH functionalization.
The next question is from Ramu Yadav. His question is, can we activate primary sp3ch bond with this catalyst?
Yes, so one of our bulkier catalysts was capable of doing primary CH functionalization, and we had a Nature Chemistry paper on that. It's not, and it goes for the most accessible primary, if there's several primary. It's not yet absolutely perfect because if there are open secondary sites, they could easily compete. But we did show that it goes very strongly towards primary in many systems, but I think there's still room for further improvement in that direction. Because I should emphasize that electronically, this chemistry prefers tertiary. Because I haven't really talked about the mechanism, but the carbene basically starts off abstracting a hydrogen. It's so electron deficient, it begins to pull a hydride away, building up a delta plus character at the carbon, and then finishing off inserting into the CH bond. So that means with a positively charged carbon, a tertiary site should be the most reactive. So the fact that we can overwhelm tertiary and even secondary to go for primary really shows the steric influence of these catalysts.
Yeah. Next question is from Symmetry. She's our master student. What are some other ways we can affect the selectivity of complex instead of steric factor?
That's a great question. So our current catalysts are relying on sterics. Okay, so then we can go for the most accessible tertiary over lots of other tertiaries, most accessible secondary. But what about the other sites in the molecule? Because we can't access those at the moment. So in terms of catalyst design, what we're doing these days is using the self-assembly to actually introduce directing groups into the wall of the catalyst, so that we will be able to hopefully be able to drive the chemistry towards not the most sterically accessible, but because it's coordinating to the wall of the catalyst, it places certain CH bonds close to the carbene. So that's where our new generation catalysts are going at this stage. That's a really good question. That's still a big challenge for this chemistry.
Yeah, another question from Rajesh Kumar. He's asking, can we use enzymatic catalysis besides using these bulky groups for CH functionalization?
Oh, that's a great question. So, and enzymatic catalysis is really a very exciting field. Obviously, Francis Arnold and several others are really doing some very interesting chemistry where they're getting artificial enzymes that can do artificial reactions. So many of these enzymes do oxochemistry, so CH oxidation, but they found that some of them can do nitrene chemistry and can do carbene chemistry. So it's really exciting what they can achieve. So they're still evolving. They haven't yet succeeded very much with donor acceptor carbenes. They're too big for the enzymes at this stage. Obviously, they'll be very interested in seeing what they can do by doing, evolution of these enzymes. And obviously, we're interested in what we can do, where we do predictive structural changes, knowing the shape of the system. So at this stage, the two approaches are complementary. Both are capable, in principle, of very high turnovers. So it's really interesting what they can do. So far, we haven't had a head-to-head competition between an enzyme and our catalysts, where they both do the same chemistry. I'm sure that's going to happen in time, and we'll see how it works out.
And one more question from Vishal Jyoti. Are these activations specific to rhodium only? Have you tried this activation with other metal-centered catalysts with a similar symmetry build?
Yes, we've looked at lots of catalysts, and some of them, our most successful was silver and gold catalysis. And you can do a lot of really interesting carbene chemistry, but they don't do very good CH functionalization. So the dirhodium seems to be really special for the CH functionalization, particularly when you're doing it on an unactivated bond. I mean, you got to remember what the carbene is doing. It's actually pulling a hydride out of an alkane. So that means that the carbene must be extremely electron deficient, okay, to be able to pull a hydride. Yet it needs to be protected somehow, otherwise you won't get any useful chemistry. And that, of course, the steric bulk of the catalyst protects what type of reactions are possible.
Yeah, one more last question I'll take, because there are many questions, so I cannot ask all questions. So last question.
Great questions.
Sir, can we use a donor-donor carbene for enhanced selective CH functionalization without affecting the steric factor?
No, that's a great question. So, every program has strengths and weaknesses. So our strengths, of course, is that we found this combination of the donor acceptor carbenes with these chiral dirhodium catalysts that can do exceptional selectivity. The weakness of our program is, of course, we have to use donor acceptor carbenes. Okay, and so one of the big challenges: how can you broaden that approach? And what we've shown actually is that a donor would normally be not reactive enough, because you need the acceptor to allow the carbene to be able to do the CH functionalization in the intermolecular sense. But it's rather interesting. We found that diaryl carbenes sort of behave. You would think of that as a donor-donor, but it actually behaves as a donor-acceptor, because the two benzene rings can't be in conjugation at the same time because they bang into each other. So one goes at right angles and behaves as relatively as an acceptor, and the other as a donor. So we've recently published about how we can do highly in anti-selective, at least cyclopropanation, with these diaryl carbenes, which is a sort of a new breakthrough. Well, we're still worried that it may not have the reactivity profile to be able to do much beyond activated CH bonds. And we're still exploring that possibility. But the challenge for our group at the moment is to broaden the range of carbene systems that can do this chemistry.
Yeah, one last question from our master students, Mohish. How electron donating group affect the catalyst?
So electron donating group in the carbene, I think is what the question. So I'm going to answer the role of the electron donating group in the donor acceptor carbene. So so the donor group is crucial. The acceptor group ensures that you've got the reactivity profile, that it can still go for the CH bond. The donor group is involved in a great deal of resonance stabilization of the carbene, and so is a critical element in terms of the site selectivity. It also is probably an important element in how the carbene actually interacts with the catalyst itself, because we have a lot of aryl groups in the catalyst. So they're probably involved in dispersive interactions with the aryl of the donor acceptor carbene and the wall of the catalyst.
Thank you, Professor Davies. Okay, finally, I would like to thank Professor Davies for taking some time out and agreeing to give this webinar for faculties and students. Professor Davies, we would also like to host you physically in our institute sometime once this COVID crisis gets over. Our next talk of the series will be delivered by Professor Gopalakrishnan from IISc Bangalore on 12th November at 4 p.m. The links to the webinar will be available on our website, and students are requested to register to avail for certificates. We will provide special certificates to students who will attend at least 10 talks of the series in a year. Finally, I would like to thank Professor Anil J. Elias, HOD of the department, and Professor Ram Ramaswamy is giving excellent guidance for us to conducting this webinar series. And also, I would like to thank Dr. Somik, who is the main coordinator and key person for this webinar, and also Dr. Bishwarup is a co-organizer. With that, I'm concluding this webinar. Once again, thanks to all of you. We hope to see you all soon. Have a great evening. Thank you, Professor Davies.
Hello.
Probably.
Hello.
Yeah, thank you, everyone. Really enjoyed being involved in this session.
Hello.
Yeah.
Yeah, thank you, Professor Davies. Thank you very much.
Sure. No, it's been great, and good luck to you, Janaki Ram. I'm sure you're going to do really well.
Thank you very much, Professor. Yeah, I think it's very early in the morning we called you. I think it's winter time was changing, no? So
That's right. I had coffee.
probably
It's okay.
it would be. Okay. Enjoy your